Hello and welcome to another IsoDec tutorial video. My name is John Pavek. I'm a postdoc in the Marty Lab, and today I'm going to be walking you through using IsoDec in the existing MetaMorpheus search engine. So not directly within the IsoDec software suite, but a useful thing to know nonetheless. So MetaMorpheus is a proteomics search engine. It does both bottom-up and top-down. And as of a few months ago, it has officially had IsoDec directly incorporated into the workflow as a deconvolution option both for MS1 and MS2 scans. So we'll just kind of walk through a search. So we need first a database. We'll do FASTA. We're going to add the contaminants. For spectra, we're just going to add one of these ribosomal proteoform fractions from E. coli. And then we get to this task screen. So this is kind of where all the business goes down. So we're going to start with a calibration method. We want to deconvolute precursors. We also want to use IsoDec for both MS1 and MS2 deconvolution. In search parameters, we want this to be top-down because it's top-down data. And you can see we have a relatively wide precursor and product mass tolerance. That's because this is a calibration method. So basically we want to find the highest scoring species and see about how far they are away from, in mass, away from the expected theoretical masses. So we're going to set that to top-down. Modifications, we need our fixed carbamidamethylation because we did alkylation here. So we're going to add that task. Then we will go to this spectral averaging task window. We're going to do the average DDA scans, which basically takes, in this case, it's 5. So it takes every 5 MS1 scans and averages them. Basically, the idea is by doing that, you're getting better signal to noise on your precursor MS1 scans, thus you generally get better deconvolution. So we're going to add that. We would like to do PTM discovery. We want IsoDec deconvolution, both in MS1s and MS2s. We're going to leave the default parameters on IsoDec. We want to make sure that our protease is top-down because this is top-down data. You can see in this case our precursor and product mass tolerances have been dropped because at this point we have calibrated, so we should have pretty good mass accuracy in this case. Fixed and variable modifications, carbamidamethylation on C, we don't need any variable ones. And then our GPTMD modifications where we have oxidation on M and acetylation and phosphorylation. Basically these I'll eventually walk through exactly what those mean once we've started the search, but I want to get that started so then we can kind of return to that. So in our search task, we want to again make sure that our protease is top down. We fix our modifications. And then we're going to go to the advanced options, and in file loading parameters, we are going to set MS1 deconvolution and MS2 deconvolution to IsoDec. And those are kind of the main IsoDec related parameters to set. We'll add that search task. And we'll just name our output folder and get that started. So What the calibrate task is doing is, with a slightly wider window, it is searching for high-scoring matches between the theoretical database and the experimental data, and finding the highest scoring ones, and using those to determine, based on retention time and M over Z, how much to adjust and in which direction to adjust or to calibrate the experimental M over Z's in your file. Now we want to do that before the averaging task, because in the averaging task, I don't know if we can actually open the parameters. So in the averaging task, it gives you a bin width. So basically the way this averaging is done is based on binning peaks between spectra and then averaging the intensity in each bin. That's at least like the very basic understanding. Basically, you run into issues with averaging if you have drift between adjacent scans. So you want to run your calibration so you make sure that everything should theoretically line up nicely, and then you want to do your averaging of your adjacent MS1 scans to get generally better precursor signal to noise. Then the GPTMD task, which stands for Global Post-Translational Modification Discovery, is basically not necessarily running an open search, but running a search with a set of allowed mass shifts to basically identify cases where you have a pretty good match between the database and your experimental spectrum, but the precursor masses differ by the masses of one of the GPTMD mods that we selected. So in this case, it's oxidations, acetylations, or phosphorylations. So we're looking for plus 16, plus 42, plus 80, and then like various combinations of those different modifications. And then in the search task, we're basically just searching each of our experimental combinations of a precursor mass and MS2 spectrum against their counterparts in the database. Each match gets a score. We're also scoring our experimental data against a set of decoy database proteoforms, basically to say what is the score distribution of our decoys against our experimental data, what's the score distribution of our targets against our experimental data, and using that to estimate confidence of our identifications. I will be back once this calibration has finished and the rest of these have finished. All right, so we are back. Our tasks have finished running, and I wanted to walk through one last thing that you can do in MetaMorpheus, which is visualization of your data. So we need to select our calibrated averaged raw file, select our PSM file, we'll load those. Theoretically, okay, we're in business. So now we can kind of click through our database matches, zoom in, see what looks good. We can also look at, let's go bigger. So we can look at sequence coverage for individual PRSMs. Let's see. So because this one is ambiguous, because it appears we were unable to localize this particular acetylation between the N-terminus and, this lysine at position 4. So we can look at the matched ions for both of those different PRSMs. We can also look at, so we can also look at, so this is our histogram of precursor mass errors. It's a lot of different things you can look at, but I figured it was worth at least touching on the different ways that you can look at data in this is called MetaDraw. So I hope that was helpful. Thank you for watching, and check back soon for probably some more IsoDec videos.